In this example, I'm going to look at an example where we'd like to do a one-sample t-test, but the data don't satisfy the normality assumption that underlies that test, and so we need a strategy to deal with that. So the data that we're going to look at is measuring biomass ratio. So we've got marine reserves that we're interested in seeing whether they are having a benefit in terms of the number of species that are in the reserves. And so this data represents 32 sites, and the site has either been protected, so it's a marine reserve, or there's a similar unprotected site that's nearby. So we're pairing these sites together, and then we're looking at the total mass of marine plants and animals per unit area of reserve divided by that same quantity in the unprotected control site. So this gives us a biomass ratio, and if there's no effect from the protection in the reserves, then that biomass ratio would be 1. If that ratio was higher than 1, then the marine reserves are having a benefit, and if it was less than 1, then the protection is actually causing biomass to go down, which doesn't make a whole lot of sense, but it's possible. So if we just take a quick look at the data, so these are all the biomass ratios, okay, and just scanning them, a good number of them are bigger than 1, some of them are bigger than 2, some of them are as much as, I think this is the largest one, 4.25, so more than 4 times as many marine plants and animals in that reserve compared with the corresponding control site. So there's only one, I think, just scanning this by eye. Is there only one? Yeah, there's only one where it's actually less than 1. So it certainly looks as if marine reserves are beneficial here. But of course we can't just kind of eyeball this and say yes, they're effective. We need to do a formal statistical test. So what we might want to do here is do a one-sample t-test and test whether the mean biomass ratio is equal to 1 or not equal to 1. So if we were to do that, we would first need to reassure ourselves that the data look as if they could come from a normal population. So one thing we could do is we could look at a histogram. So that does not look like a nice symmetric bell-shaped distribution to me. It's skewed. There's a very high peak in the middle, quite a big tail out this way. Doesn't look very normal to me. Another type of plot we can look at to assess normality, because it's a little bit subjective, saying is that a symmetric bell shape or not, but a slightly easier way to graphically assess normality is to use something called a normal probability plot, or a normal quantile plot, or these are sometimes called QQ plots. And so let me just draw one and then we'll talk about it. So makes more sense if when you draw a QQ plot or a normal quantile plot like this, that you make the plot square, and so this piece of code will make the plot square, and then this draws and in R they do call it a QQ plot. In the book it's called a normal quantile plot, and in other circumstances you'll see this referred to as a normal probability plot. And what we do is we add a diagonal line to the QQ plot, and the way that you interpret this kind of plot is you ask yourselves, do the points lie along the line? And if they do, then you can be assured that the data may well have come from a normal distribution. If there's a big divergence, which there is here, because the points are along the line kind of in the middle, but they're way off the line up at this end, and a little bit off the line down at this end. So if you see this kind of pattern in a QQ plot, it should raise a red flag, and you should start to question whether the data could have come from a normal distribution. We can also do a test here known as the Shapiro-Wilk test, and if we do this test, it's a hypothesis test, so we've got the usual 4 steps, but I'm going to go through this quite quickly because I don't want to spend a lot of time on it. But essentially, the null hypothesis here is that the data is normal, and the alternative hypothesis is that the data are not normal. The test statistic, let me run the piece of code so we can look at the test statistic. This is the test statistic here. I'm not gonna dwell on how that's calculated. We're just going to use this test quickly to assess normality, and so we're just going to say, okay, this is the test statistic. Step 3 is what's more important here for our purposes, and that's the p-value. So step 3 is the p-value for the test, which is this number here, 8.851 times 10 to the minus 5. It's very small, almost 0. And then step 4, make a decision, draw a conclusion. Make a decision. The decision rule, it's always the same with any hypothesis test. If the p-value is smaller than the significance level alpha, which we generally set at 0.05, then reject the null hypothesis in favor of the alternative. If it's not, then we cannot reject the null hypothesis. So in this case, we get a really small p-value. It's less than 0.05. And so we reject the null hypothesis in favor of the alternative. Remember, the null hypothesis here is that the data are coming from a normal distribution, and so we're rejecting that, and so we're affirming what we see in the plot over here. This Shapiro-Wilk test is agreeing with our visual impression of the normal quantile plot, and a normality assumption isn't really very tenable here. And so if that's the case, we should not be using a one sample t-test. And so at this point you might go, oh, well, we're stuck. We wanted to use this test and it relies on this assumption, and we're not sure that that assumption is valid. So we're stuck. But there are things that we can do. So there are paths out of this, and one possibility, it's something that works sometimes it doesn't, it's always worth trying, is to apply a transformation to our data, and then perhaps the transformed data will satisfy the normality assumption. So that's what we're going to do here. If I just go back to the histogram for a second, I mentioned that this histogram has a skewed quality to it. Okay, this tail on the right is kind of a long tail, longer than the tail on the left. Data that's skewed like this, with a long tail on the right, can sometimes be transformed into a variable that looks more normal using a logarithmic transformation. And a logarithmic transformation, what it tends to do is it pulls in really high values and spreads out low values. And so let's try that in this case. So we'll apply a logarithmic transformation. We're going to use a natural logarithm transformation here. There's different types of logarithm transformations, and the most common one in statistics is a natural logarithm transformation. So that's calculated using this code here, using this log function. If you're not sure what the base is for the log transformation that you're doing, you can look at the help and just read what it's doing here. Log computes logarithms, by default natural logarithms. Okay, so it's doing the logarithmic transformation we want, because we want a natural logarithmic transformation. If we wanted to use a different base, there's an argument for that. Okay, so we've transformed our data. Let's go through the steps we just went through. Let's look at a histogram of the transformed data and see if it looks a little more normal. Well, relatively speaking, relative to this distribution, this one was highly skewed. This one, it's still a little bit skewed because this upper tail, it's bigger than the tail on the left. So it's not quite symmetric, but it does have a little bit more of a bell shape to it. Can I say for sure that this data could have come from a normal distribution? At this point, not really, because I'm still relying on a subjective notion of whether this looks like a bell shape or not. So maybe a QQ plot, a normal quantile plot, would help things. So let's do that. We'll make the plot square. We'll draw the normal quantile plot, and then we'll add the diagonal line. And now, well, it's not great. I must admit that it's not great. Ideally, we want the points to lie a little bit closer to the line than they do. These ones are all good. So now this lower tail, it's okay. And it's okay all the way up to here. And then these last, 1, 2, 3, 4, 5, 6 points, a little bit further away from the diagonal line than I would like. Way better than before, though. Before we had this, these points were a long way from the line, and even in the lower tail we were off the line. So now we're better. The question is, are we good enough? So let's do the Shapiro-Wilk test and see if we're okay now. Okay, let's go through the steps again real quick. Hypotheses. Null hypothesis is the data are normal. Alternative hypothesis, the data are not normal. Test statistic, 0.93795. P-value, step 3, 0.06551. Step 4, decision and conclusion. Decision rule, reject the null hypothesis in favor of the alternative hypothesis if the p-value is smaller than the significance level. If we're using a significance level of 0.05, we're not smaller than that now. We're just slightly above it, 0.06551. So we cannot reject the null hypothesis here. And the null hypothesis is that the data are normal. So we're okay. Just. This is a little smaller than I would like, but we're just about okay with believing that it's possible that the data could have come from a normal distribution. It's not the most normal looking distribution I've ever seen, but it's actually close enough for our purposes. Okay, so now we have a variable that does look like it comes from a normal distribution. And so now we can do a one sample t-test. So I'm actually not going to go through these steps this time. This is doing the calculations by hand. But by now, hopefully you're comfortable enough with a one sample t-test that we can actually skip to using the t.test function because it's a lot quicker. And so let me just quickly look at the help for this. So if we look at the arguments here, what I want to look at is this. So mu, this stands for the Greek letter mu. This is the value of the mean in the null hypothesis. So when we first looked at the data up here, we were looking at whether the marine reserves were beneficial, which would mean that the biomass ratio would be higher than 1. But we did a natural logarithm transformation. Okay, so now what we're interested in is whether the mean of the log biomass ratio is equal to 0. And the reason for that is because if you take the natural logarithm of 1, you get 0. Let me just show you that. Natural logarithm of 1 is 0. Okay, so now we're not testing the mean of the biomass ratio equal to 1, we're testing the mean of the log biomass ratio equal to 0. So running through the steps, because we're doing a hypothesis test. Null hypothesis, the population mean is 0. Alternative hypothesis, the population mean is not 0. Second step, test statistic. Let's run the code and see what it is. 7.3968 for the test statistic. P-value, step 3. P-value 2.494 times 10 to the minus 8. Step 4, make a decision, draw a conclusion. Decision rule, same as ever, reject the null in favor of the alternative if the p-value is less than the significance level. Otherwise, do not reject the null hypothesis. So we have to ask ourselves, is the p-value less than 0.05? Yes, it is. It's essentially 0. So we therefore reject the null in favor of the alternative. And the alternative hypothesis is that the mean log biomass ratio is not equal to 0. And that was what we suspected. We suspected that marine reserves were beneficial here because we're getting biomass ratios that tend to be bigger than 1, and we've just demonstrated by doing this test that we have statistical evidence for that conclusion. We can also calculate a 95% confidence interval. And so if we ran this code here, we would get a 95% confidence interval for the mean log biomass ratio, going 0.347 up to 0.611. If I undo the transformation, get it back into the original units for the biomass ratio, I have to apply the opposite transformation to a natural logarithm, which is exponentiating. So if I use this function here, exp, and put 0.3470180, that's going to give me the lower bound for a confidence interval for the biomass ratio. And then if I do the same thing to the upper bound, 0.6112365, there's the upper bound for the confidence interval for the mean biomass ratio. I can do this all in one shot if I use this code here. So these are the numbers that I just calculated. So we're 95% confident that the mean biomass ratio is between 1.41 and 1.84. And so this entire interval lies above the value 1. So again, this is statistical evidence that what we were thinking when we looked at the data is borne out by a statistical analysis, that marine reserves do appear to have benefits in the sense that the biomass ratio is above 1. So that's an example where we wanted to use a one-sample t-test, but we couldn't because the data didn't look normal. But then we applied a transformation, and the transformed variable did look normal. So then we could apply the one-sample t-test to it, and then at the end we back-transformed the confidence interval back into the original units, and we're able to get a confidence interval for biomass ratio, the mean biomass ratio.